Hello there and welcome to another part of Module 2. We'll be continuing with the basics of computer organization and design. In this video, we'll be covering the topics of computer registers, and we will also look at the common bus system for a basic computer organization. Starting with processor registers, we will be looking at how many registers are there in a processor. So a processor has many registers that hold instructions, addresses, and different data and all. The first register we'll be referring to is the program counter. The task of the program counter register is to store the memory address of the next instruction. So when a program is being run, the instruction that is currently being executed, the next instruction that is supposed to be executed is stored in the program counter. Okay. The second instruction, the second register is the instruction register. This is the one that stores the instruction after it has been read from the memory. So when we run a program, what we do is we fetch the instruction from the memory. So once we fetch it, it is put into the instruction register for further execution. The third type of register is the address register. This is the one that stores the address that the memory is locating. Okay, and it helps in keeping track of which locations in the memory are being addressed. It uses either direct or indirect addressing, and this is what the address register is used for. When an operand is found, okay, using either direct or indirect addressing, the operand that is to be used for performing the operation on will be stored in the data register. So the fourth register is the data register, which stores the operand, and the operation will be performed on the operand, because the processor then uses this value as data for its operation. And finally, there's another register called the accumulator, and this is for the manipulation of data. So what happens is whenever we perform any operation, the manipulated data or the result is stored in the accumulator by the processor. We also have the temporary register. So often a processor will need a scratch register to store intermediate results or temporary data. So whenever a instruction is being carried out, sometimes there are sub answers that need to be further operated on. Hence they'll be stored in the temporary register. We also have the input output operations. So input devices are considered to send characters of data to the processor, and processor can send characters to the output device. For this we have the input and the output registers, for short called INPR and OUTR. The input register holds characters from an input device, and the output register holds characters to be sent to an output. Here is a summarized table of all the registers. This is a necessary, it's a important thing that you need to learn. You need to know the sizes of the registers and their symbols. The function is easy since most of the names are related to the functions. A data register holds the operand, it holds the data, and it is 16 bits in size. The address register holds the address of the memory that is being used, and it is 12 bits in size. The accumulator is a register that is a processor register which stores the manipulated data. It is 16 bits in size. Instruction register holds the instruction code, 16 bits in size again. The program counter holds the next instruction or the address of the next instruction, 12 bits in size. The temporary register is 16 bits in size, and both the input and output registers are 8 bits in size each. In this we can see the format of representation of the registers in a register form. We had seen we can write registers with their name in the middle and the number of bits on the top. We have our PC, we have AR, we have IR, TR, OUT-R, INP-R, DR, AC, and we also have the memory. We have the bits defined for each of them, and this is another way of writing down the registers. The memory is of 4096 into 16, where 4096 words and 16 bits of each word. We get 4096 from the following: 2 for binary, and then we have power 12 for the address of the code. The instruction format in the instruction code has 12 bits of address, so we have the memory size accordingly. And then, as we can see, 12 bits of an instruction word are required for specifying the address of the operand. while 16 is the total length of the instruction code in bits. So since the memory stores the instructions, we have the following specification accordingly to be able to fit the instructions into it. We have 3 bits left, and that are for the opcode or the operation part. This is the instruction format: 12 bits for the address, 3 bits for the opcode, and 1 bit for the mode. There is the representation for the instruction format, and the last bit can be used to specify the direct or indirect address. Coming to the next topic, we will be understanding the common bus system. So this topic will refer to since we've seen a basic bus system of how we can connect different registers and take a common register from multiple registers. We studied that in module 1. In this system, what we'll be studying is how the common bus system is applied to a basic computer system. The basic computer model has 8 registers, 1 memory, and 1 control unit. We studied the 8 registers. Okay, to transfer information from one register to another and between the memory, paths are required. Okay, so for transfer of information from one place to another due to the execution, we need paths. And if individual and separate connections are made, it would become very complex and it would be messy. Plus, it would be really hard to update the system and see and make any changes to it because it becomes extremely complex. A more efficient scheme is by using a common bus system, because a common bus system becomes a common line for all registers. So it's just one line that connects every single register together. The connections of the registers and the memory of the basic computer to the common bus is done by multiplexers or 3-state buffer gates. We studied this in module 1 as well. We will be using either one of these, and first we will study the basic structure of the bus system. So we arrange the memory unit on the top, then we place the registers in the following order. We have the address register, the program counter, the data register, the accumulator, the input register, the instruction register, temporary register, and output register. It is very important that you try to understand the bus system properly, because many questions will be based on this, plus further topics are also related to this system. Now this is the common bus that we will be using. Since the biggest number of bits that we have in our registers is 16, the highest number of bits is 16, the common bus system will be used for 16 bits. Had it been any smaller, there would be loss of data, because the most significant bits of the 16 bit registers would be lost. There will be the control inputs S0, S1 and S2 in the bus, which will help us to decide which register will be selected to load onto the bus. The selects that will choose which register or memory would use the bus, and we have the adder and logic circuit over here that will help us perform adding or logical operations, and the E is the extended bit that holds the carry. So if we are performing addition instruction or anything, then the carry bit will be stored in the E extended bit. We have now connected all the registers to the bus. We have also added some different instructions. We will refer to them one by one. First, let's see how the registers are connected to the bus. So the memory unit is connected to the bus at level 7. The AR, PC, DR, AC, IR and TR are connected to the bus as well in 1, 2, 3, 4, 5, 6 and 7. We can use binary values of S0, S1 and S2 to determine which of the following will be allowed to use the bus. Hence we can say that 111 values of S0, S1 and S2 will allow the memory unit to load onto the bus, and similarly 001 will allow the AR, 010 will allow PC and so on. We do not, as we can see, we do not have the 0th part. The sequence counter 000 will be showing the instruction that none of them are being loaded onto the bus. That means none of the registers are using the bus. So at the 0th selection, none of the registers will be using the bus. The next part is that we have to see all the registers are connected to a common clock. This is a master clock, a general clock that is connected to the output temporary input instruction register AC, DR, PC, and AR. All of these are connected to the clock. This determines that at which clock cycle what instructions are to be carried out. The AR and PC are 12-bit registers. Rest all of them are 16-bit. Okay. So in the 12-bit register, when data is transferred to the bus, the most significant bits are set to 0. So the last 4 bits of the addresses will be set to 0. We will also look at the two operations of the memory unit. We have the write operation and the read operation. So these allow us to either write into the memory or read from the memory. The rest of the registers have three in different operations: LD, INR, and CLR. LD stands for load, INR is for increment, and CLR is for clear. These three operations allow us to perform certain tasks to the register, which we'll be discussing further. The other side of the bus shows input towards the registers. So not only can we take data from the registers, but we can also transfer data onto the registers. This is only possible when the load option of the registers is set to 1. So if we take AR for an example, if the load of AR is set to 1, the binary value 1, then only we are able to transfer data from the bus to AR. As we saw previously, the selects S0, S1 and S2 select the register or memory that would use the bus. Load, whenever enabled, the particular register for which the load is enabled will receive data from the bus during the next clock transition. That means that once the clock cycle in which the load is made 1, once that clock cycle is over, the next clock cycle is when the data will be loaded onto that certain register. E is the extended bit. It is a flip-flop that holds the carry from the arithmetic calculations. The registers DR, AC, IR and TR are 16 bits. AR and PC have 12 bits, and that is because each of them hold a memory address, and the memory address is only 12 bits long. When the contents of AR or PC are applied to the 16-bit common bus, as we said, the four most common bits, the most significant bits, the MSB, are set to 0. When AR or PC leave information from the bus, then only when they receive information, from the bus, only 12 of the least significant bits are transferred, and the four MSB are discarded. The input and the output registers communicate with at least 8 bits, 8 significant bits in the bus, since their size is of only 8 significant bits. The input register receives a character from the input device and it transfers it to the AC, which is the accumulator, while the output register receives character from AC because data manipulated is stored in AC, and then it delivers to an output device. 5 registers have 3 control inputs: LD, INR and CLR, where LD is for loading, INR is for increment. So in case we need to increment the value of the registers, we'll use increment, and clear is to clear out the registers. Here we'll be looking at the practice problem where it says a computer uses a memory unit with 256k words. So 256k over here means 256 into k stands for 1024. So 256k words of 32 bits each. A binary instruction code is stored in one word of the memory. Okay, the instruction has 4 parts: an indirect bit, an operation code, a register code part which specifies one of 64 registers. So the register code part is specifying one of 64 registers, and an address part. So in this section we can see that the instruction has 4 parts. Previously we studied 3 parts. So this is the difference that is made when a designer designs it according to their requirement. In this question we have been given with 4 parts, which is the indirect bit, that means it will be only 1 bit. The operation code, op code we have the register code which specifies to one of 64 registers, and an address part. The part A states how many bits are there in the operation code, the register code and the address code. So we need to find out the number of bits. In B we have to draw the instruction word format, and we have to show the number of bits in each part. And in part C we'll be determining how many bits are there in the data and address inputs of the memory. Since the memory unit has 256k words of 32 bits each, we can say that 256k where k being 1024 can be split into powers exponents, where 2 power 8 stands for 256 and 2 power 10 stands for 1024, hence the summation 2 power 18. We can also say that since there are 64 registers, the control will be 2 power 6, which gives us the output of 64. Thus the address is of 18 bits because of the words and bits multiplied, because we find it out from the number of words. Again, the address of 18 bits. The register code is 6 bits, because what the register code does is it gives the sequence of bits that would allow you to choose from the number of registers. In the previous examples we had a 3-bit register code, so that would allow, if we have a 3-bit register code, it will allow you to choose from 8 different examples. And since we have 64 different registers over here, then 6 selection bits will be there. The indirect bit is 1, hence since you can see there is 32 bits per word. Okay, so 18 plus 6 plus 1 is going to give us 25, and the difference from 32 will give us 7 bits, which will be for the opcode. Since we already found 3 parts, the 4th part is the opcode, hence the remaining bits are for the opcode. When we put it into the instruction format, we will write the addressing mode, then we'll mention the opcode, and as we have address in the end, we can mention the register at this point. Since there are 32 bits in all, we can mention the number of bits for each part on top of the representation. 1 bit for addressing mode, 7 bits for opcode, 6 bits for the register selection, and 18 bits for the address size. Finally, the data has a total of 32 bits and the address part has a total of 18 bits. Here we have solved a question on the instruction code format for a given numerical. Here we have another question where it says the following control inputs are active in the bus system. So we studied the bus system for a common computer system. We will be using that bus system to solve this question. For each case, specify the register transfer that will be executed during the next clock transition. So if we have part A, B, C and D, each of them are separate instructions. So if this is the case, what are the instructions that will be executed, what are the operations that will be carried out, and that's what we have to determine. First we will draw the bus system. We will be addressing to this bus system. Since in part A we have selection lines as 1, 1 and 1, we can see that this refers to the number 7, and if number 7 is selected, that means that the memory unit can use the bus system. Our next step is to look at the load part. So for the IR, which is the instruction register, we have load as that is set to 1. Hence IR will have load set to 1, which means it is capable of receiving data or getting data loaded into the register. Finally, we have memory set to read. This means that the memory will be read and the instruction from the memory is going to be copied into the bus, and it will be transferred all the way towards the IR where load is set to 1, and hence that will be the operation in part A. The memory will find the instruction copied to the bus, and then the bus will load it onto the instruction register. In B part, we can see that we have the code 110. In this way we can find out the register that will be working at 110, where 110 stands for 6, which is the temporary register. Hence the temporary register's data will be copied onto the bus, and then we can see that the program counter has load set to 1, so our program counter will be ready for loading information onto it. And since we have nothing to do with the memory or the adder, there will be no operations there. We can see that the temporary register was copied onto the bus, so in the next clock transition we can say that the data will be transferred to the program counter and it will be loaded onto that. In part C we have 100, which refers to the operation of 4. 100 is for accumulator. The accumulator register will be loaded. Since 100 bus is connected to accumulator register at point 4, we can also see that the load of the data register is set to 1. That means whatever data is loaded or copied from the accumulator to the bus will be loaded onto the data register. Now one thing to take care is that the memory is also set to write. So whenever the memory is set to write, that means the data in the bus will be written into the memory. Hence, in this case, not only will we have it being loaded onto the data register, but it will also be added to the memory. So two things are happening here. And as we discussed earlier, whenever the sequence counter is 000, the selections, none of them will be selected to load onto the bus. But we have AC, the accumulator, having load set to 1. That means AC is ready to get a value, and the adder is set to add. This means that the adder will be performing the addition of any input number, and for that there are two possible inputs. Either the input register will send input to the adder logic, or the data register will send. Okay, so we can mention either one of them that will perform addition, and they will load it onto the accumulator register. To compare our answers, we can see in part A, memory is read from to the bus and it is loaded onto the instruction register. Hence, memory is loaded from there to the instruction register. In part B, the temporary register is loaded to bus and then it is loaded to PC. Same way in part C, AC to bus and then it is written to memory and it is loaded to DR. So AC goes to bus and it goes to memory as well as DR. Finally, add DR or the input register to AC. So addition using the input of DR or the input register, either one of them, into AC. That's it. Thank you for this lecture and see you in the next video.